making the numbers better, editing the budgets and stuff like that. What a terrible waste of talent for all these mediocre tasks.
Okay, let's go ahead and get started then. So today's seminar speaker is Amy Roberts from the University of Colorado, Denver. She's just recently started as a professor there, which is wonderful. She's one of our colleagues on Super CDMS, and I will give her a warm Texas welcome.
Awesome. Well, thank you guys so much for having me, and also for stopping by after lunch. So I'm going to be talking about detectors. I'm a detector person, and I'm going to be talking about how exactly the Super CDMS detectors work. And I, of course, think how the Super CDMS detectors work is fascinating. But in particular, what I'm going to be talking about is exactly what we measure and how that's related to the physics happening inside of the detector. And this is becoming more and more important as we start building the next generation of experiments. And so that's pretty much the talk. So, you know, if you're busy, you've got it all. Okay, so let's go ahead and get started. So, I heard that there were going to be a mix of students and professors in the room, and possibly not everybody was going to be, strictly speaking, all dark matter all the time. So I just wanted to very briefly mention what dark matter is and why we're searching for it. Okay, so this is a problem that is probably familiar to many of you, but just in case. So what happens when we look out at the galaxies and estimate how much mass there is in a galaxy? So it turns out that there are multiple ways to do this. One of the ways that astronomers have gotten very good at is looking at the light coming out of the galaxy and estimating what's in the galaxy based on the light that's coming out of the galaxy. And so you can estimate what's in the galaxy based on the light, and based on that, you can predict what the mass of the galaxy is, and you get a number. Great. And then you can measure the mass in other ways. And so here is shown in some data a rotation curve. So the rotation curve is related to how much gravitational pull there is in the galaxy. And we think we understand gravity. Great. And so we can use this rotation information to, together with our understanding of gravity, to predict how much mass is in the galaxy. There are other ways even than this to predict how much mass is in the galaxy if you have a cluster of galaxies, gravitational lensing. But this is sort of the beginning of the problem. And so you get another number, and these numbers do not match. So that's the problem. So when you estimate how much mass is in the galaxy based on the light that's in the galaxy, you get a number that is much smaller, about 5 times smaller, I think, than how much you get when you measure using other methods like the rotation curve or gravitational lensing. And so the question is, what's going on? It appears that there's more mass in the galaxy than we can see, and so that's where the matter comes from, and if we can't see it is where the dark comes from. So this is sort of the mystery that kicked off people starting to look for extra mass. Okay, so there's a lot of, when you go trying to solve this problem of there seems to be more mass than the light is predicting, it turns out you can come up with a lot of different potential explanations. So I'm not going to get into all of these different potential explanations. I just want to emphasize that there are a lot of potential explanations. What we see here is a simulation right alongside a measurement. And so when we assume that there is a weakly interacting, not a weak force interacting, not capital W weakly interacting, but just a particle that doesn't interact very often, that's massive and cold, or cool, or maybe even just only a little bit warm, you can get a universe that looks very similar to the one that we measure. And so this is the lambda CDM theory, this cold dark matter. So we need some kind of matter that has some mass, that doesn't interact very often, and that's not moving too fast so that galaxies can clump around it, and it can clump around itself. I guess the clumping around itself comes first, and the galaxies clumping around it comes later. Okay, so this is what we're looking for. And there are a lot of potential particle explanations for this. And so the real point that I want to convey on this slide, this is all kind of small font. But the real point that I want to convey on this slide is, again, there are a lot of potential candidates to explain this missing mass. The candidate that the dark matter community historically hasn't exclusively focused on, but a lot of the focus in the dark matter community has been on this candidate right here, which is just one of them, of course. And so this is this weakly interacting massive particle. So it sort of satisfies the criteria that it's not moving very fast, according to the theories that would potentially make it. It only interacts weakly, that's a capital W weakly. So it doesn't interact very often, and it's massive. And so that fits what we need. There are other things that don't move very fast, don't interact very often, and have mass. And so those are also all candidates. But the super CDMS detectors were originally designed to sort of optimize their sensitivity to this particular type of candidate. And so the thing that is useful to know when you're trying to optimize your detector is the mass range. So why is the mass range important? We're going to talk about that when we look at our detectors. So let's talk about how you actually build a dark matter detector. So we think maybe there's some kind of dark matter particle, and we would like to try to detect it. And so we need to think about how it's going to interact. So if you're building a detector to sense a weakly interacting, so it interacts via the weak force, massive particle, then what you have is you need a detector of matter, which is pretty easy to grab here. So matter is convenient for this because matter consists of protons, neutrons, and electrons. The protons and neutrons and electrons all have weak charge, so they're all going to interact with a weakly interacting particle. The downside to something that weakly interacts is that the weak interaction is a short-range interaction. So this is a really good mental model for a weakly interacting massive particle interacting in our matter detector. So here we have a weakly interacting massive particle hypothesized coming in and then bouncing off of normal matter. And typically, when you're talking about GeV scale WIMPs, the kinematic energy transfer to the nuclei is going to be much, much better than the kinematic energy transfer to the electrons. And the likelihood of it hitting is also much higher. So the reason that I'm mentioning this is because one of the points of this talk is that the dark matter, the super CDMS detector started out being optimized for this heavier GeV scale dark matter. And we've been looking for it, and increasingly we've been improving our detector technology. And so as that's happened, we've lowered our threshold, and that makes us sensitive to lighter and lighter particles. And so the reason that this is significant is, or that I mentioned all of this, sorry, it's hard to find the leave button here for me. Okay, so the reason this is significant is because often we've talked about our signal as looking like a particle hitting a nucleus. And increasingly, people are starting to think about, well, the electrons, they also weakly interact. And so you could have a very light mass come in, and it would have a better energy transfer to the electrons. And so a lot of times, when you see trying to separate signal and background, you're trying to separate nuclear recoil from electron recoil, and that's because for a heavier WIMP, you're much more likely to get good energy transfer to our nucleus here. But that's less and less the case when you start considering these lighter particles. Okay, so we just need some normal matter, and then if our particle, as long as our massive particle is weakly interacting, and we're patient, we should actually be able to see it. And so the other question here is, should we actually be able to see it? So do we actually expect a particle with a mass about the scale of a GeV to kick a germanium atom, or a germanium nucleus in particular, enough that we could see it with existing detector technology? And the answer is, yeah. If you have about 70 GeV WIMP here, for example, then you're going to get a good solid 10 keV energy transfer. Now, that's the case where the WIMP is coming in and is hitting the germanium nucleus dead on. And so that's a direct energy transfer there. Of course, you're much more likely to have a glancing collision. And so a glancing collision is going to deposit significantly less energy into your detector. But at least at least our maximum allowable deposited energy isn't below current detector technology limits. Okay, so we need normal matter to detect something weakly interacting. We think that there's some chance that we'd actually be able to see something in a mass range that seems relevant. And then the other question is, how often will we see it? And I'm going to skip this for now. We'll come back to this later. And how often will we see it? And so the answer is not very often, but maybe if we wait for, on the scale of years to 10 years, we may actually be able to see some signal. Okay, so I just want to sort of give a little bit of some background on the new facility that we're going to be building in. So CDMS has operated for the past 10 years at the Sudan mine up in northern Minnesota, and we decommissioned earlier this year, I think. And so we're in the process of building the Generation 2 experiment, and the Generation 2 experiment is going to be, a little tough to see here, but it's going to be in a deeper mine. So here's where we were at Sudan, and we're going to be moving down to the Sudbury Snow Lab. And so this is a picture of the rock that's going to encompass our new facility. And then here's our new, so far we haven't started cutting metal on this yet. And so then our detectors are sitting right inside there. And then here's someone gleefully observing genuine detector pulses. So this is what we're going to look at, is exactly how do these detectors operate. And so what I want to, the point of this slide is that I'm not talking about background at all in this talk. And so all of this is to shield us from background, of which there is a lot. Feel free to ask me after if you're interested in knowing more about that. But we've got other things to discuss. So, okay, so what do the CDMS detectors actually look like? They're shiny, they're germanium crystals. They fit in the palm of your hand, and they feel fairly heavy. And they are operated cold, very cold. So these are 50 millikelvin, and we'll see why here. Okay, so the basic principle of operation for our detectors is that we have a particle that comes in and interacts somewhere in the bulk of our crystal. And so that is going to knock either an electron or a nucleus. And so that electron or nucleus that starts moving is going to generate phonons. So that's going to create some vibration in the lattice. And it's also going to liberate some electron-hole pairs. So germanium is a semiconductor, so depositing energy into it can excite electrons and holes above the band gap. Now, what we do is we apply a voltage, a small voltage. So germanium detectors are often operated at kilovolts, but we apply, on the scale of 5 volts. And in our high voltage mode, we apply on a scale of 100 volts. So we apply some voltage, and that means that the charges are going to drift. And then as they drift, they're going to deposit further energy. And so then what we do is we put some sensors on the top of this. Now, I've only drawn one of the types of sensors. So we actually have sensors that are sensitive to phonons, and we have sensors that are sensitive to charge. The charge is just a wire. And so it's less interesting, and I'm not going to discuss that one in detail. But the way that the phonon sensors work is the electrons here are going to end up creating phonons as they travel along, and the phonons can heat up this small piece of metal that we have glued to the surface. And so here's our small piece of metal right here, this little yellow blob. So that's our tungsten. This right here is one of the reasons that we need to operate our detectors at such cold temperatures. So we want to keep this little tungsten blob hanging right in between superconducting and non-superconducting. And so then when a phonon hits, so I'm simplifying here. So the phonons these are very small, so the phonons aren't very likely to hit it, but the idea is that the phonon is going to deposit energy, and then that energy is going to make its way to the tungsten. And since it's right on the edge between superconducting and not superconducting, even that small amount of energy is enough to change its resistance. So our real sensor right here is just a variable resistor, a very sensitive variable resistor. And so this is the circuit that we have. We have a variable resistance. And so when that resistance changes, the current going through this leg of the circuit is going to change. And we read that out with a squid array. And we see the change in current over time, right here. So something happens in the detector, and then we warm up a small piece of tungsten, and that changes our current, and then that is what we actually observe. Okay, so given this, there are sort of two kinds of questions that we can ask with our detectors. So one optional question is how much energy was just deposited in our detector? So we can look at these pulses that are coming out, and if we have more energy deposited in the detector, we'll see larger pulses. Less energy transfer, we'll see smaller pulses. So we can ask exactly how much energy was there. But another question that we can ask with these detectors, and the reason that we can ask this is because we have these two channels. We have information about the charge and information about the phonons as well. We can ask whether or not the particle interacted with the electrons or the nuclei. And so this is a yes-no question and is much lower background than this question. So we can sort of do two different types of analyses with these detectors when they're operated in a traditional mode. Okay, so how do we actually go from there was something deposited, something happened in the detector, and then we estimate some energy based on that. So the event site right here is quite small. And what happens when it first collides is we have some prompt phonons from the shaking of the lattice. And then we also have these charge carriers drifting. So we sort of talked about that already. And so the thing that happens here is that as these charge carriers drift, they're in an electric field, but because they're in a semiconductor, they have some maximum velocity. So what they have to do is they have to shake off that additional energy in the form of these loop phonons. And so then that is what so the prompt phonons and the loop phonons that the moving charge has shaken off is what we actually sense with our phonon sensors. Okay, so equation-wise, what that looks like is our total phonon energy ends up being the phonons that come from that initial collision that are prompt, and then we have the number of electron hole pairs that are created times the energy that they gain from traveling across that voltage. So this is this direct contribution, and then we also have this loop phonon contribution. And so this is where the questions start. So the question that we need to ask when we're thinking about what energy was deposited in our detector is how many electron hole pairs actually got created. The way that we model this is we say, well, okay, so we have some energy that comes in and hits a nucleus, say. And so that's going to give that nucleus some recoil energy. That's what this E sub r indicates. So then we say that, well, so given a certain amount of energy, it's going to take a certain amount of energy to create an electron hole pair. And so that is what this E sub gamma is indicating. So we have this estimate for how much energy on average it takes to create an electron hole pair. And then the yield says how much of this energy that's available to create electron hole pairs actually goes into creating electron hole pairs versus going into creating phonons. So this right here sort of describes what the coupling is between the hit and the electronic system. So here we have the number of electron hole pairs. Is the yield multiplied by the average amount of energy that's available for creation of electron hole pairs. Okay, and so then what the yield allows us to do, we can calculate how much energy actually went into electron versus phonon creation. And what we see is that for hitting a nucleus, we end up with less of the recoil energy going into the electron system, the electronic system, whereas for a hit to an electron, most of the energy goes into the electronic system. And so this is how we're able to discriminate between electron recoil and nuclear recoil events in the CDMS detectors. And what you can start seeing here is an indication a little bit of a problem. So at some point, these bands, so you can sort of see these rough bands right here, At some point, these bands start crossing and we lose the ability to discriminate. And that's at a fairly high threshold. Okay, we'll come back to this. Okay, so what I want to point out is that threshold. So here is a picture of what the expected energy distribution for different mass WIMPs would be. And so what you can see, if you focus here on this 50 GeV, this right here is a typical threshold for for example, the super CDMS Sudan detector operated in normal load, where we are trying to discriminate between electron recoils and nuclear recoils. And what you can see is that plenty of the PDF is above our threshold. But if we're interested in looking at 2 GeV WIMPs, that energy distribution lies entirely below our threshold. So we have the ability to discriminate between electron recoils and nuclear recoils, and that's very powerful. But we also pay a price in having a somewhat high threshold. So what we can do is we can instead, we can increase the voltage to about 100 volts of our detector, on the order of. And by doing that, we can lower our threshold significantly. But when we do that, we lose the discrimination between the electron recoil and nuclear recoil that we had. So we lose information, but we dramatically lower our threshold. And we also fundamentally change the question that we're asking when we look at our data for our detector. So whereas in this case, we can clearly see what the nuclear, whether or not a particular hit was a nuclear hit or an electron hit. In this case, we don't know. We just know, the only thing that we know is how much energy was deposited. And so that means that we're in this land of having to look at some kind of a spectrum and say, okay, well, this is what we expect the WIMP spectrum to look like. And we can look at the spectrum that we measure. This is a calibration spectrum. So this is not the spectrum that we measure when we're really searching for WIMPs. But how many WIMPs could the measured spectrum potentially emit given the energies that we measured? So in this mode, energy deposition and understanding accurately what the energy deposition is really critical. But it also gives us more reach. Okay, so here's what that reach looks like in practice. So here we have, so this is a projection for SNOLAB. And what you can see is over here, we have these detectors operated in this lower voltage mode where we can still discriminate between electron recoil and nuclear recoil. And over here, down with access to 0.5 GeV WIMPs, we have the detectors operated in this high voltage mode where we can no longer discriminate, so we lose our information, but we are able to see much lower energy depositions. Yeah, okay. So that's what the interest is and why we would be willing to give up that additional information, because we get a lot more reach with the threshold. Okay, what could possibly go wrong? Nothing. Okay, so what we are starting to look at is we are starting to look at very small energy depositions. And the reason that we're excited about operating our detectors in this high voltage mode is that it allows us to see these very low energy depositions. So whereas in a traditional CDMS experiment, we would, say, have an analysis threshold on the order of a keV or 2 keV, when we operate in this higher voltage mode, we end up with an analysis threshold on the order of hundreds of eV or tens of eV. So the super CDMS, CDMS light analysis that we recently did, the lowest analysis threshold for that set of data was 56 eV. So at 56 eV, you start needing to consider, well, the energies of your atomic system start becoming significant relative to the energies that are actually being deposited in your detector. And so historically, what we've done is we've pretended like when a dark matter particle comes in and hits a nucleus, it's hitting a free nucleus that's just in vacuum, and we ignore the crystal part of it. And that's fine if what you're depositing is 2 keV, right? Because atomic binding is on the order of 10 eV, so who cares about 10 eV? But when we are starting to look at these very low energies, this isn't a great plot to illustrate that. When we're starting to look at the scale of 56 eV, then the difference between 10 eV and 20 eV to knock a nucleus out of its lattice site could start becoming very significant. And again, the type of question that we're able to ask with these very low thresholds that we achieve is what energy was deposited. So we need to know that energy very precisely, and if we don't understand what that energy is, then that introduces significant error into our estimates, into our limits. Okay, so here's I just wanted to sort of, I don't know, this is a nice little demonstration that that there really are atomic effects that influence how things lose energy in our solids. So this is a tungsten paper where they're doping tungsten. And so this is of a lot of interest to the semiconductor industry. So they often want doped semiconductors. And so you use ion implantation, for example. And so what the semiconductor industry is very familiar with is the fact that if you orient where you're shooting your ions differently along the crystal lattice, you'll have very different penetration depths. And so that's what this plot is sort of showing. It's saying that here, if the ion implantation is oriented, you have amorphous tungsten, then you end up with an average depth that's pretty small. If you orient the ion implantation with respect to the 110 axis of the crystal, you end up with this significantly larger implantation depth. And then over here, at a full order of magnitude away from the amorphous tungsten, you end up with a very deep penetration depth if you shoot things along the 100 axis. I think this makes a lot of intuitive sense. If you try to kick something and it's going down exactly in a space where there's like a lot of room, it's going to travel farther, and that's practically speaking what we see.
But this shows that how far the ion goes in the crystal.
That's correct.
Not how far the ejected ion.
That is correct. That is correct. Yeah. So, but what? That's right. Yeah. Yeah. So the what this is really saying is that the energy loss of a particle traveling in the crystal can be different depending on what direction it's moving in. Whereas we traditionally assumed that the energy loss does not depend on the direction that it's moving. Okay. So we talked about the yield here. So our energy, the total phonon energy that we measure, it depends on how many prompt phonons are created. Not too much can go wrong with that. And then here we have the number of electron hole pairs that are created. So, and then we multiply that by the energy that we get from each electron hole pair when it drifts across the entire detector. So if we are wrong about the number of electron hole pairs that are created, then our energy calibrations can end up being significantly off. And so here, this yield, this factor that tells us how much of that deposited energy goes into the electron system versus how much of that deposited energy goes into the phonon system, we've got measured data points. So this right here is showing what the yield is. And what I want to point out here is that it stops at about 300 eV. And so the CDMS light results that I mentioned, again, that threshold is on the scale of 56 eV. So we extrapolated for that. There are several dark matter experiments actually that have been doing some measurements and those sort of suggest that this prediction that we're making could be off by a significant amount. Okay, so what can happen is we don't create the number of electron hole pairs that we think we do, and that can affect the reconstructed energy that we have for a particular physics event. So that's one thing that can happen. So understanding the yield is really critical. I am going to skip this for now. And so another thing that can happen is we can get Freckle defects. So what our detectors are sensitive to, fundamentally, is how much charge there is and how many phonons there are. So if we have energy that goes away in some other form, we're blind to it. One of the ways that energy can get lost in a detector is you can end up with an ion, your ion that's traveling. So you hit your germanium nucleus and it travels away, and then it's going to stop somewhere. And the place that it stops might be at a different energy than the place that it started. So what you can end up with is you can end up with a crystal that has a net like positive energy, right? So your crystal is taking away some of the energy of that interaction. And that's not necessarily something that we can see because it would need to fall back into its lower energy state and make some phonons for us, and then we can see it. But if it's just going to stop there and hang out and not create any phonons and not create any charge, then we're not going to be able to see it. And then we're going to reconstruct the energy thinking that we got all of it, but actually some of it has vanished. So this is another way where we can end up having error in our reconstructed energy on now when we're looking at these very small energy scales, a scale that matters for our energy spectrum. Okay, so Freckle Defects is one. Okay, so this is just sort of a brief tour to sort of demonstrate that there are things that can go wrong here. And then really the question that we would like to answer is, well, okay, so we don't know what the yield is down at these very low energies. How do we measure it? And so there are experimental efforts towards this, but there are also theoretical efforts. And so I just want to mention some of the theoretical efforts. So this is, let's see if this works. Yeah. Okay. So we're not the first group of people who want to understand how energy in a system is divided into the motion of that, so the physical motion, so the phonon motion of the system, and the electronic system. So computational chemists have been looking at similar problems for quite some time, and some of those tools we can directly use. Okay, so this is an example of somebody who has studied a problem that's very similar to our problem. So one of the problems that computational chemists have looked at is how do you understand how materials degrade when you put them really close to, say, a nuclear reactor? And so if you want to understand how materials degrade when they're close to a nuclear reactor, you need to have some kind of model about how the structure of that material is going to change, or how it's going, right? If you have something that comes in and hits it, what is the final state? And so that's great, because that's exactly what we want to know, right? We have something that's coming in and hitting our germanium, and we want to understand how the energy is dissipated in the system and where that germanium ion ends up. And so it turns out that this is a fairly complex computational problem. So the reason that this is a complex computational problem, if you really want to solve this fully quantum mechanically, we're not dealing with fast stuff, so relativistic, at least for the ions, isn't so important, but the electrons can move pretty fast. So if you want to understand the system and make as accurate a model as you can, what you're going to find is that you can't make your system very large. So if you want to do a fully quantum mechanical, fully relativistic simulation, you are going to be able to put together like a system of 4 by 4 or 9 by 9 atoms. And even though we're depositing small amounts of energy, we still expect our ions to move a fair distance. And so doing the computational chemistry trick of using periodic boundary conditions and repeating the lattice is fine as long as you don't move outside of the box that you're using as your period. But if you are depositing even tens of eV, your box needs to be bigger than 4 atoms. So there are actually a couple of reasons for this. So one reason is that it will travel somewhat far. But even if you have an ion that's traveling a very short distance, what we're interested in is what part of that energy goes into the electronic system. And so if we want to model that accurately, we need to have a system large enough that the electronic band structure is modeled accurately. And so that means, that means a lot of atoms. So a lot of atoms is tough to deal with, but there are methods to get around this. So you can do for example, combination of classical and quantum mechanical treatment, where you treat the motion of the ion classically and take the quantum mechanical solutions for the electron system at multiple steps. And so that's what these guys have done here. This is the Ehrenfest method. And one thing in particular, so I want to point this out, it's really cool. What we're looking at here is we're looking at a time evolution of a moving ion in a metal. And so what the colors mean is what the ionization state is, how much charge is associated with that area, what the electronic density is. And so what you can see is that the ion is moving along and it's sort of developing more and more charge density as it goes along. The reason that this is particularly interesting is because the model that we have used in the dark matter community is the Lindhardt Model. And one of the assumptions that the Lindhardt Model makes, and other models like it, is that the ionization state of the ion remains constant. And in fact it doesn't. So there's new information that we can get. So even though this particular simulation is not a fully quantum mechanical, fully relativistic, all interactions considered, right? So this model, for example, is not considering electron-electron interactions because that's really difficult to do. So even though it's a pared down model, it still is telling us something very useful about how the ion is moving through the system and how the electronic system is responding to that. So there's hope. Okay, so this is essentially a repeat of what I've said. So here we have very simple models, and over here we have much more accurate and atomic scale models. Over here, if we want to go for the most accurate models that we have that we can write down, we can only model a few atoms with them, and that makes them not of a ton of use to us. And then over here, we have some sort of a continuum model where you treat the electrons as an electron gas, and those can treat very large systems, but they're missing some of the features that we know are present in these crystals that we believe will be important for really accurately understanding what the response of the detector is. And so the real point of this slide is that there is a middle ground where we can learn how our system is responding a bit more accurately, and we can still actually do those computations. And so here I just wanted to point out some local work that's been done. This is one of these in-between models applied to dark matter specifically. So what this is showing is that when you have, if I explain this incorrectly, please let me know. When you have your incoming dark matter, that's going to be at some angle relative to the axis of the crystal. And what this is showing is what the threshold of the detector is for incoming dark matter at a particular angle. And so what this is saying is that if you had a dark matter beam, if you could create a dark matter beam and shoot it just at one particular angle, your detector would have one threshold, and if you could orient that differently, the dark matter beam relative to the crystal, you would have a different threshold. And so practically speaking, what this means is that the detector is going to have a different response depending on the angle of the incoming dark matter. And here you can see sort of, so this is a combined density functional theory approach, sort of with using some classical potentials to make the computation faster. But what you can see is that it still is reproducing this sort of directional effect that we might expect. And the energy scale that the simulation suggests that this is over is over a scale of 15 to 55 eV. So the thing I want to point out here is that this is a computation that's possible, and we see a significant energy variation, especially considering that our snow lab detectors, we are targeting to have 10 eV phonon sensitivity. So this is on a scale that is very, very relevant to our Generation 2 experiments. And you can potentially do some interesting stuff with this. If the angle of your WIMPs on average changes over a year, then you're going to have one part of the year where your detector has a lower threshold than another part of the year.
It's actually daily.
Ah, great, okay.
It's orientation, which is even stronger.
Yeah, yeah. Yeah, you don't have to wait for a whole year. That's wonderful. Okay, so I'm going to, let's see, I have 15 more minutes about. Is this a, Okay. All right. So I'm not going to talk in detail about this, but what I want to mention is that simulations. Here we have a simulation. Here we have a simulation. I don't know what your guys' experience of simulations are, but it's great to be able to compare them to data in my experience. And so these simulations, we need to be able to compare them to data to really be able to have faith that when we go to reconstruct the energy that was deposited in our detector, we are doing it correctly. So a lot of assumptions and a lot of estimates and a lot of approximations go into all of these models, and so getting quantitative information out of them is certainly possible, but it's a really good idea to check. And so CDMS and other experiments, but I know about the CDMS efforts, so we'll sort of stick to them. So CDMS has numerous efforts going towards calibration of our detectors. So what we have is we have a situation where we have some detectors that are sensitive down to these levels. So I think it was at SLAC, Stanford and SLAC, they have a demonstrated detector that has sensitivity down to 10 eV phonon resolution.
Actually 0.1.
0.1 eV phonon resolution. Okay, thank you. So single electron hole pair. So we can tell when a single electron hole pair has been created in this detector. So this is really sensitive. And so this is the sensitivity scale where we start being able to measure these kinds of effects. So what we have is we have some detectors that are actually sensitive to this energy scale. And then we have facilities where we can put in a beam of known neutron energy. And so we can hit it with a known energy and then watch what happens. And so that sets us up well for taking some data to not only calibrate our detectors, but also understand more about these in-between quantum mechanical, classical, computational models that could help us with our energy reconstruction. Okay. So I think this is, I'm really excited about this. So I'm really excited that we are starting to have detectors that are sensitive to atomic scale physics effects. I think that's going to be really interesting to participate in. But I want to mention at the close of the talk some of the ways, again, that this very low threshold helps us with physics. So if we have a very low threshold and we really do understand our detector response, what are some of the things that we can do with that? So certainly we can continue our search for dark matter. This is one option. Even GeV scale dark matter approaching, if we're interested in setting limits on smaller GeV scale dark matter, like 2 GeV scale dark matter, we're starting to be in a realm where we need these very low thresholds. And so this will give us increased sensitivity to that kind of dark matter. But one of the things that I mentioned at the beginning was when we have a detector made of ordinary matter, it's got nuclei and it's got electrons, and both of those are weakly charged, and so our potential dark matter candidate could interact with both of those. So people are increasingly starting to look at what it might look like to have a very, very light mass dark matter particle that's scattering off of the electrons in the detector. And so this here is a plot by the Xenon collaboration. And so what this is showing is the number of electrons that are kicked free after an interaction in their detector. And so this is a 1 GeV dark matter particle. And so what you can see here is that you're sort of expecting quite a few cases where one free electron hole pair is what we expect, and then maybe 5 and 6 is another maxima, but very few electron hole pairs. And so with very low thresholds, we can be sensitive to this kind of signal. And they've actually released a limit for these very low thresholds. I'm not sure that it's based on data for their smaller scale experiment, I believe. Okay, so Dark matter in general. We can access lower mass dark matter, and we can even start accessing very, very low mass dark matter that would predominantly interact with electrons. This is not an exhaustive list by any means, but then the final thing that I'll mention is not actually a dark matter candidate, but fractionally charged particles. So fractionally charged particles, no one's particularly ordered fractional charged particles at this point, but we can do searches for them. And we've done a search with CDMS detectors. I'll talk about that very briefly. But this is a case where, with a much lower detector, we can start increasing our sensitivity to fractionally charged particles fairly dramatically. And so the fractionally charged particles that I'm talking about in this case are not slow fractionally charged particles. They're very energetic fractionally charged particles. So these are not dark matter candidates, but this is still physics that we can do with our detectors. Okay, all right, so I'm gonna tell you a little bit about this search, and then I'll take questions. Okay, so when I say fractionally charged particle, what I'm talking about in this case is I'm talking about something energetic, and that's just the analysis that we decided to do. And I'm talking about a particle that has a charge of something like e over 10, or e over 100, or maybe even e over 10 to the 8th. So right here, we can sort of see the parameter space for this. So here we have the fractional charge, and then over here we have the lip. These are often called lips for lightly ionizing particles because they don't ionize as much as a normal electron would. And so here we have the lip mass. And what you can see is there's a lot of parameter space over here where no limit has been set at all. And so with these lower thresholds, we think that we may be able to do analyses that have some sensitivity to very small fractional charges. So with fractionally charged particles that are energetic, there are two different types of analyses that you could imagine doing with the CDMS detectors. So one of the analysis tools that we have is we have in the CDMS detectors, we have several CDMS detectors all in a stack. So each green block is one CDMS detector that's instrumented with all of its phonon sensors. So separate phonon sensors for each one of these. So what you can look for is if you have a particle that has some charge and might be ionizing, it has some chance of depositing energy in each of the detectors that it passes through. And so what you can look for is you can look for a signal where each of these detectors in this stack has seen some energy deposition. But that energy deposition is less than the energy deposition than you would expect, for example, from a muon. And then the question is, well, okay, so if you see energy deposition in each one of these detectors, and that energy deposition is less than a muon, what are your possible options? You could, I suppose, have a neutron that scatters and scatters and scatters and scatters. And it turns out that's very unlikely. And also the energy spread is going to be very substantial. So if you have a fractionally charged particle that's ionizing and not slowing down very much, the amount of energy that it deposits in each of these detectors is going to be fairly consistent. Whereas scattering from a neutron or scattering from a gamma is going to have a wide spread in possible energies. And is also really, really unlikely. It's hard to find a gamma that will scatter successively in six sequential detectors. And even harder to find a neutron that will do that. So this right here is sort of akin to the CDMS classic mode, where we operate and we're able to separate electron recoil from nuclear recoil, and we have a very low background experiment. So this is a case where we have a very clear signal and very little background. So this is a really lovely experiment to do, and certainly benefit going to a lower threshold. But another type of experiment that we could do is we could just look at one detector. We could just look at one detector and we could say, well, we think we know what energy will be deposited by a particular fractional charge. And so we can look at the energy spectrum of this one detector, and we can ask how many of these fractionally charged particles could potentially be hiding in that spectrum that we measured. So that also is a very similar question to the question that we ask when we do a CDMS light or a high voltage style analysis, where we're asking how much energy was deposited in our detector and how much does our measured spectrum look like a WIMP spectrum. Okay, so we have these two different styles of analyses that we can do. And this right here is a result from a paper done using this tower style analysis, where what is required in order for what would be required, no events were found. What would be required, I should say that, we didn't see any events that deposited energy in all of the detectors with significantly less energy than a muon. That would have been pretty cool, but we didn't see it. Okay, so that's what we're looking for here. So in order to have qualified, an event would have had to deposit energy in each of these detectors, and it would have had to deposit a similar amount of energy in each of the detectors. Okay, and so this is the limit that arises when you get no events off of that very low background experiment. And so what I want to point out is this bend right here. So what's happening with this bend right here is because we're requiring that energy to be deposited in all of the detectors in this tower, we pay a heavy penalty when the probability of the energy deposition starts getting much less than 1. Because we pay a penalty to the power of 6. Okay, and so what's happening right here is this is about the charge right here. So E over 10, E over 20, E over 30, those are still charges that are quite likely to deposit an energy above threshold in a detector. But once you get out to E over 50, you are starting to get significantly less likely to deposit energy over threshold in a given detector. And so that's when you start seeing this limit get significantly weaker. Okay, so let's look at that parameter space. So again, the reason that this is an issue is because there's all this uncovered parameter space. So this study was able to set a limit sort of out to E over 200, but there are no limits in this range of very, very small fractional charges. And so we could certainly extend this limit, but it's going to start not fitting on the plot very well. And so what we're asking is, well, is there a different way we can use our detectors to give us a little more sensitivity out in these very small charge regions, very small fractional charge regions? Okay, and so then the answer is, well, yeah, we can do exactly what we do with the WIMP limit. If we have an experimental spectrum, and again, this is a calibration spectrum, so it looks a lot like a calibration spectrum, but if you have an experimental spectrum and you know what your energy deposition should look like, then you can ask how many of this kind of particle could potentially be hiding in your experimental spectrum. And so to do this, you need your experimental spectrum. You really need to understand what your signal spectrum is going to look like. That's important. That's what we're working on, we're focusing on right now with this. And you also really need to know what your detector response is. And if you know those things, then you can set a limit that is where instead of a very sharp rise right here, you will have a much more gradual slope. And so it gives you a bit more reach for these very, very small fractional charges that no one has been able to look at before. Okay. So what I want to point out about this is that this is exactly like a WIMP analysis. And really this is the kind of analysis that we can do with anything where we know what the expected energy spectrum will look like due to that particle. And so the power that we are starting to come into with these very low threshold detectors is that anything that has a tendency to deposit a small amount of energy instead of a large amount of energy is something that we are able to dramatically increase our sensitivity to by lowering our threshold. Well, how dramatically depends on what the shape of the expected energy distribution looks like. But there's a lot of stuff that likes to deposit just enough energy. Right? You're often much more likely to deposit a small amount of energy than you are to deposit a large amount of energy. Here what we're seeing is this thing wants to deposit one electron hole pair or none. And so by getting these detectors that are sensitive down to one electron hole pair, we start getting a lot of purchase on this PDF. Okay, all right. So this is sort of a summary. I think I just summarized this looking at an actual data slide, so I'll kind of leave it there. But we've got a lot of mysteries, and we are starting to look at these lower and lower energy scales with our analyses. Right, we don't know what mass scale to look at, and so it's really important to be able to look at these lower masses. And as we do that, we are starting to run into these atomic scale effects that we need to be able to address to really be able to accurately reconstruct the energy that's being deposited in our detectors. And that energy reconstruction is particularly critical for these kinds of analyses because we are looking at the energy distributions and comparing them to the expected energy distributions of our target particles. And then the other thing that I just want to close with is that this applies to dark matter, it applies to light dark matter, but it also applies to neutrinos and fractionally charged particles and anything that we know the energy distribution function for. So that is everything, and I just want to say thank you, and this is a list of the Super CDMS collaboration, and so all CDMS light and very, very sensitive phonon detectors, all are brought to you by the great members of CDMS. So thank you guys all for your time.
Questions for Amy?
I have a quick question. So on the molecular diagrams, you were talking about the simulations also, the scale of dynamics and so on. Have you found inconsistencies with what they found with the thresholds and so on? Or
Inconsistencies with?
In terms of threshold, do you find similar results with the threshold of detectation or you haven't gone that far?
So I haven't gone that far with this. Yeah, yeah. In this particular study that I mentioned, it wasn't looking at threshold. So this is why I mentioned your paper, because there's a limited there's not much that's directly applied that work to the dark matter community. Yeah, yeah. No. So but yeah, I would be very interested to take the work that they did with metals and try to port it over to our semiconductors.
Because one of the advantages, it's just a comment on the question, once you get that threshold, that level of energy, then you can use the defect actually to discriminate with variables on that particle, because you can look at a spectrum and see that there's a shift of the Freckle Defect energy in the spectrum.
Yeah.
That gives some features.
Is that something that you can do event by event, or
No,
is that something that you need an aggregate? Yeah. Okay. Right. Right. Yeah.
Other questions? All right. Let's thank Amy again.